Thank you.
Thank you very much. So good morning, good evening, good afternoon, good night, whatever applies to the participants of the meeting. What I'm going to talk about is the joint work with Giselle Monteiro, who is also in the audience. I have seen her name, Vincenzo Recupero. And so this work was mainly done within my project, which I'm running at the Faculty of Civil Engineering of the Czech Technical University. So my affiliations are a bit complicated. Now, there is a question mark in the title, and the people who know me, they certainly guess what the answer will be. And so I will start it something that basically everybody probably knows. Prox regular sets in the Hilbert space X. And so there is a formal definition. So essentially, the set Z, which is here represented by the green area, is called the Prox regular. If there exists an R neighborhood of the set, so this pink layer, this is the R neighborhood of the set Z, in which there is a uniquely defined projection. So points in the red layer have a unique projection in Z. So I take a point Y in the R neighborhood of Z, and I find a unique point X on the set Z. And so this is a formal definition, and there exists also a variational definition in terms of a variational inequality. Scalar product y minus x, x minus z, plus the norm of y minus x divided by 2r times x minus z squared greater or equal than 0 for every test element z in the set capital Z. Okay, and so this is the Prox regular sets are the sets for which we can define projections, at least in the neighborhood of the set. So I denote by capital Q the projection. Again, there is the variational characterization of the projection. And I also define the distance mapping D, which is the complement of the projection. So D is the vector which connects the projection to the original element. And of course, the norm of the D of Y is the distance of the element Y from the set capital Z. Now, what is interesting that the distance mapping is local Lipschitz continuous. So if we take 2 points which are away from the boundary of the admissible layer, then the distance mapping is Lipschitz continuous, but the Lipschitz constant depends on how far we are from this set Z. So if you are very far, if you are very close to the boundary, then but this is to be expected that the Lipschitz constant of the distance mapping is big. Now, there are some further interesting properties. So there is a kind of superposition formula that if we take the projection of y plus delta dy, then we get again the projection, the same projection, which in terms of the distance mapping is translated in this superposition formula, which turns out to be useful then when constructing solutions to our sweeping processes that I have not defined yet. Then another interesting property is that the distance mapping is a gradient of something. So it is a potential mapping. And this something is 1/2 of the distance squared. And I will also mention the case of sublevel sets, and which I define as a set. So if I define Z to be the set of those elements of the Hilbert space X where a function g of z is less or equal than 1. So in the convex analysis, this would be the gauge, but I don't assume any convexity. I only assume that the gradient of g is bounded away from 0 on the boundary of z. And then it is possible to prove that set Z is R Prox regular R depends on the properties of Z, which I will mention in a moment. Now, discrete sweeping processes. We will consider sets which depend on an additional parameter. So we will have two inputs. We will have one input which will describe the translations of the set Z, and then another input value which describes the change of the shape. So W will be the measure for the shape, and we assume that Z of W depends continuously on W in terms of the Hausdorff distance, which so I recall the definition of the Hausdorff distance, and continuity is, so for every epsilon there exists delta, standard definition of continuity. And now, discrete sweeping process. So we consider two inputs. I will explain the physical meaning of the inputs. So we have two sequences, Uj in the space X, Wj in the space of parameters, which can be a Banach space, or for example, and we prescribe an initial condition x0 and Z of W0, and define recurrently xj to be the projection on ZWj of xj minus 1 plus uj minus 1. And I will show a picture in a moment. And clearly, the sweeping, we are not allowed to run out of the admissible neighborhood of the sets ZWj. So we have to assume something about how far we can go from uj minus 1 to uj and from wj minus 1 to wj. And the sufficient condition is that the sum of the two contributions is smaller than R, and then the discrete sweeping process is well defined. And now, so, and this is related to the catching up algorithm. And my example refers to the Gerson model of fatigue. So we interpret, so the input uj is the strain, xj is the elastic strain, which is assumed to be limited to the set Z of wj. So Cj is the plastic strain. So we decompose the strain into the elastic strain, which has to be bounded within the set Z, and then Cj is the complement. And Wj is the fatigue parameter. So the set in terms of the Gerson model, the set depends on the current value of the fatigue parameter. And now, so what is happening? So we are at the time j minus 1, we have our elastic strain somewhere in the set Z of wj minus 1. And now we apply a strain increment, uj minus 1. And now, so we run out of the set Z wj minus 1. What we do in the next step, that we take the projection of this point, but not on the on the set Z of wj minus 1, but on the updated shape, xj. So xj will be the projection. So again, we change the set and we project on the new value of on the new set Z of wj. But of course, in the Gerson model, the fatigue Wj is assumed to be proportional to the dissipated energy, which is the total variation of the plastic strain increments. Which means that our sweeping process will be implicit. So, so the Wj is not really an input. This is an artificial input, and at the end I will show that this problem can be solved by a kind of fixed point principle. So we will first study the sweeping processes for W given, and then I will show that under suitable assumptions, it is possible to solve the Gerson problem as it is originally stated, the fatigue measured in terms of the energy dissipation. And now, so again, I come back to the variational inequality, which defines the projection. This is exactly what what the variation inequality is doing. And so the xj minus 1, xj minus z. So again, xj plus xj is uj. Minus z, then there is the quadratic term corresponding to the describing the non-convexity, and this has to be satisfied for every test element z in ZWJ. Okay, so this is the discrete case, and we would like to pass to the time continuous case. And now, so look at these two expressions. Xj minus 1 appears in the scalar product, and it appears also here in the norm. So one might expect that now I divide by the time interval, I let the length of the time interval tend to 0, and I get xi dot. And so this is what should be the continuous version of the sweeping process. But of course, this cannot be done that easily. The limit is not so obvious. And actually, I don't want to pass to the limit. I would like to find a formulation of the sweeping process which would include both the continuous version and the discrete version. And for this reason, I have to give a proper meaning to the time derivative in quotation marks. So it can be the difference of the consecutive solutions. This can be a derivative, or this can be something else. And so let me say that this is the variational inequality formulation is perfectly equivalent, again, equivalent modulo the interpretation of what is xi dot. But if we omit for the moment the question about what is xi dot, then formally this is perfectly equivalent to the standard definition of the sweeping process with the normal cone to a convex set C of t, because our set C of t here now is nothing but u of t minus z of w of t within the interpretation related to mechanics, to the Gerson model. So this is I prefer the formulation in terms of the variational inequality, because it is, in my opinion, more flexible, and you will see in a moment why I insist on that. And there are many references, many people have worked, and we have learned a lot of things from the people that are listed here. I would particularly thank to Giovanni Colombo, who introduced us into the topic of non-convex sweeping processes. Now, so what will be our functional framework? Regulated functions. I recall the definition. The function is called regulated if the left and right limits ut minus ut plus exist for every t. And I denote the set of regulated functions by capital G with values in X or values on W. This makes no difference. I just mentioned that this is a Banach space with respect to the subnorm, and this is a closure of piecewise constant function, of step functions. So step functions constitute a dense subset of this of the space of regulated functions. And people working in stochastics also use the name CADLAG for continuous regulated functions. This is an abbreviation for continua droite limite à gauche. So maybe you are more familiar with this, but it is exactly the same object. And now this is something that I aim at, that to extend the non-convex sweeping process to inputs which are only regulated. And I claim that this is possible under some assumptions that I will specify later, that this can be done via the Kurzweil integral variational inequality. And so, so the dxi stands for xi dot, dv of xi stands for absolute value of xi. So V is the variation of xi. And this is the Kurzweil integral formulation of the variational inequality. I have to probably to mention, to make a short introduction into the Kurzweil integral. The main ingredient of the Kurzweil integral is the concept of partitions and gauges. Now, so this is a kind of a Riemann type integral in principle. So the philosophy is very similar, but there is one substantial difference which I will emphasize in a moment. Now, so we take an interval AB, we take a division of the interval AB, division points are T0, T1, etc. And with the division, we associate partitions. And partitions is an element of the partition consists of one interval of the division, Tj minus 1 and Tj, and one element chosen in the interval Tj minus 1, Tj, which I call the tag, tau j. So tau j is an element Tj minus 1, Tj. So up to now, this is exactly the same what the Riemann would do, but there is a there is the point which is different from the Riemann construction. I define the set gamma of AB. This is the set of all functions which are positive on the whole interval. When I say all functions, I mean really functions. So this is in the Kurzweil integral theory. There is the concept of almost everywhere plays no role at all. So there is no almost everywhere. There are no measures. So when I say function, I mean function defined at every point. And then so a gauge, any function which is positive everywhere can serve as a gauge. And now we say that the partition delta is delta fine if the whole interval Tj minus 1 Tj is contained in the open interval tau j minus delta tau j plus delta tau j with some specifications. And now the Kurzweil integral. So we define the Kurzweil integral sum over a partition delta to be f tau j g tj minus g tj minus 1. So this is exactly the Riemann-Stieltjes formula, but the definition is different. So we say that j is the integral a to b ft dgt. If for every epsilon there exists delta, a gauge delta, such that for every delta find partition j minus the integral sum is less or equal than epsilon. So this looks very similar. I will show you in a moment the difference with respect to the Riemann construction. But so what we can see immediately is that the Kurzweil integral is linear with respect to both f and g. This is a bit more complicated to prove that it is additive with respect to the integration domain. Means that integral from a to b plus integral b to c is equal to integral a to c. This is not for free. So the proof is quite involved, but it is true. Otherwise, we would, this would be problematic. Now, the comparison between the Riemann-Stieltjes integral and the Kurzweil integral. So these are the integral sums that I represent by areas of the green rectangle. So for the moment, you see no difference at all. The pictures are exactly identical. The integral sums are perfectly identical. But what the Riemann-Stieltjes integral requires is that this sum is stable with respect to shifts of the tag. So you have to be able to shift the tag within the interval Tj minus 1 without changing substantially the value of the sum. In the Kurzweil formulation, it is exactly the opposite. We keep the tag fixed, and we have to guarantee that the integral sum is stable with respect to small shifts of the division point. This looks like a small difference, but it is a huge difference. So for example, every Lebesgue integrable function is Kurzweil integrable. So it is more general than the Lebesgue integral. Just this easy trick. Now, and let me say something about the properties. So for example, what we are interested in, that the integral f dg exists if f is regulated and g is bv, or if f is bv and g regulated. So this is something that you would have difficulties to interpret within the Lebesgue integral, because G does not necessarily have bounded variation. It is enough if F has bounded variation. Now we have an integration by parts formula. So there are the standard terms FBGB minus FAGA, but then there are all the contributions on jumps in the whole interval AB. But this is, of course, this sum is finite because the regulated functions have only countably many discontinuities. And now the substantial feature of the Kurzweil integral is the behavior with respect to convergences. So if we have a sequence of regulated functions which converge uniformly to F, and another sequence of regulated functions which converge uniformly to Gn, which converge to G, and for example, the variation of Gn is bounded independently of n, then the integrals converge to the integral f dg. And now I come back to our non-convex sweeping process. So we assume that an additional condition, what Giovanni Colombo and Manuel Monteo Marques, I think they are both here. So hello, Manuel, hello, Giovanni. We have learned from you this internal cone condition, because so for people who work in convex variational inequalities know that in order to keep the total variation bounded of the output, we need non-empty, the interior of the set be non-empty. Here we need something more. Non-empty interior is not enough. We need a stronger condition, and I will show a picture. So the condition says that for every point x, we have to be able to, so there exists d and s, we have to be able to find a point x star at distance d, such that if we draw a ball around x star of radius s, then the whole cone is contained in the set z. So our set z on this picture does not satisfy the intercone condition. Intercone condition is violated. Every cone intersect the boundary. The cusps are not allowed. So even though the set Z has non-empty interior, it does not satisfy the cone condition. We cannot hope for any bound for the variation, because imagine an input which oscillates along the horizontal axis, then the output stays here, and the total variation of the distance function will be unbounded. It will be the same as the output variation of the input variation. Okay, so non-empty interior cone condition. And now we restrict ourselves to right continuous inputs in order to make the things simpler, but this is, okay, I will comment on that later. So again, we are given a function u, which is regulated. We look for a decomposition. So u again corresponds to the total strain. We want to decompose it into the elastic strain and plastic strain, and such that x of t is an element of z of w of t. So w is given for the moment, and the variation inequality is satisfied for all regulated test functions, elements of the admissible set z of w of t with the given initial condition. And the result is the following. If u and w are right continuous piecewise constant functions, then, and satisfy the jump condition, then the piecewise constant function x given by the catching up algorithm is an exact solution of the Kurzweil integral variation inequality. So it is different from the original Moreau approach to sweeping processes, because for Moreau, the catching up algorithm was an approximation. He did not have any solution for the, he did not have any equation for the solutions of the catching up algorithm. But we say that this variation inequality is satisfied exactly if Uj and Wj are piecewise constant, and the piecewise constant solutions constructed by the Krejčí algorithm satisfy the equation at every point. Good. And now, we want to we want to use the Kurzweil integral convergence theorem. So what the strategy is that now we have solutions of the problem for piecewise constant functions. So we take any right continuous regulated functions u and w, we approximate them by piecewise constant functions, we pass to the limit, and the only thing we have to guarantee that the functions xn have uniformly bounded variation. And if the interior cone condition is satisfied, then it is indeed possible to prove that the plastic strains xn have uniformly bounded variation, and so the convergence, the Kurzweil integral convergence theorem gives us the solution. And it costs nearly nothing to prove that the solution operator, which with the inputs u, w, and initial condition x0 associates the solution xi, is continuous with respect to the supernorm. And okay, so we have seen that the Kurzweil integral variation inequality is good for piecewise constant functions. It is good for regulated functions, provided again a jump condition. So we have found a magic number here. So it has to be smaller than, definitely smaller than r. I don't know if 5 is optimal or not, but for r over 5 it works. Now, what happens if the inputs are more regular? So for example, the cone condition is not needed if the inputs have bounded variation and if the Hausdorff distance function is Lipschitz continuous. Then we have a bound for the total variation anyway, and we don't have to refer to the cone condition at all. Now, what is more interesting is that if u and w are absolutely continuous, then the Kurzweil, and again, you have to prove that the solution of the Kurzweil integral variational inequality with inputs u and w absolutely continuous, that the output is absolutely continuous as well, and that the pointwise variational inequality is satisfied in the almost everywhere, because we are in W11. So again, so if the Hausdorff distance is Lipschitz with respect to the parameter W, and u and w are in W11, then the solution is in W11 and satisfies the classical variational inequality almost everywhere. But again, this is a consequence of the Kurzweil integral variation. So the Kurzweil integral variation inequality now gives a unified recipe how to define a solution of a non-convex sweeping process. Now we can say even more if the sets are smooth. How do we define the smoothness? So in terms of the gauge G. So we assume that Z of W is a sublevel set of a smooth function G. And so, for example, if G is continuously differentiable, in the Hilbert space, the proof is not so trivial, but it can be proved that for a continuously differentiable function G, the set Z of W is R-prox regular, and we can even find an estimate for R. This is C, the lower bound for the X gradient of G, and then kind of Lipschitz continuity of the gradient. And what is more interesting is that in this case, not only that for inputs in W11, we have the output in W11, but we have strong convergence. If UN and WN converge strongly to U and W in W11, and also the solutions converge strongly in W11. And in even the smoother cases, we have a local Lipschitz continuity of the solution operator. So not only that the gradients are continuous, but the partial gradients of the gauge G and with respect to X and with respect to W, if they are both Lipschitz continuous, then the solution mapping is locally Lipschitz continuous with respect to the W11 norm. And we have even an almost explicit formula with some constant AGBG, which depends only on the properties of the function G, the gradients, the Lipschitz constants of the partial gradients. So we have a Lipschitz continuous dependence on smooth sets with respect to W11 norm if the set is smooth. Now, why the W11 norm and the SUP norm are so important? Because these are precisely the norms which are preserved with respect to time transformation. So rate-independent problems typically work well in spaces whose norms are compatible with the time transformations. So the W11 norm and the SUP norm are invariant with respect to time transformation. And this is the reason why rate-independent problems have good properties with respect to D space. So for example, we cannot expect any Lipschitz continuity in any, even in 1D. The one-dimensional play is not Lipschitz continuous in W1P for P bigger than 1. And now, and since we have Lipschitz continuity, we can think about using the Banach contraction principle to solve an implicit sweeping process, state dependent. So that W is a function of, can be a function of U, it can be a function of Xi of the input, it can be a function of the variation of Xi. So this would correspond, this choice would correspond to the Gerson model. The W depends on the variation of the plastic state. And with the, and so obviously something has to be, in order to use the Banach contraction principle, something has to be small. And so the gradient of H with respect to Xi and the gradient of H with respect to V, they have to be sufficiently small, in particular if the Lipschitz constant is big. And then in this case, not only that the implicit sweeping process has a solution, but the solution mapping is again locally Lipschitz continuous in W. So the Gerson model, for example, can be included. And now, there is another kind of implicit problems in the literature. Very often you see problems like minus Xi dot of T, element of the normal cone to C of T of Xi of T, plus another source term G of T and Xi of T. But again, if you rewrite it in terms of the variation inequality, we are about to solve the implicit problem, Xi equal to the solution operator of the Kurzweil integral variation inequality with input V, where V is U plus integral G of T and Xi of G of tau, Xi of tau d tau. So again, the Gronvoll argument will work. And then what we are currently doing, viscous approximation. So this is our variation, Kurzweil integral variation inequality. We take a regulated, we consider a fixed domain Z, and we replace the variation inequality by a singularly perturbed equation epsilon Xi epsilon dot equal, and now to a function of the distance multiplied by the distance mapping. So a typical example would be Fs equal to S. This would be the Yoshida approximation. And the goal is to let epsilon tend to 0 and prove that in the limit we get the solution of the Kurzweil integral variation inequality, which is almost true. Now, so F is an increasing function. I forgot to say, increasing convex function. If it happens that f prime is continuous and f prime of 0, f second of 0 is 0, then the differential equation that is written here is a smooth gradient flow. So this is again an information which is of interest. And now the main theorem is that if Z is R-prox regular, satisfies the interior cone condition, and then the input jumps are again bounded by something. I don't guarantee that the denominator 5 is optimal, but at least it R over to 5 it works. Then the solutions of the singular perturbed differential equation, independently of the function f, converge to the solution of the Kurzweil integral variation inequality, more precisely to the left continuous representative of the solution. And what is interesting is that the values of u of t are absolutely irrelevant. They are completely forgotten. The only thing that matters at jumps is the difference between u of t plus minus u of t minus. The value u of t at the point t has no influence on the limit. And now I'm coming to the end. So Kurzweil integral. So I was trying to convince you that with the same Kurzweil integral formulation, we can treat both the time discrete and time continuous setting of the sweeping process. This gives, in my opinion, an elegant description of discontinuous evolution because we have a unique formula for continuous and discontinuous. We have straightforward convergence properties in time discretization schemes. This is what, for example, when you combine PDEs with hysteresis and when you do time discretization, it is very convenient to use the Kurzweil integral formalism as well. And the Kurzweil integral calculus is amazingly simple. So it is, you really have to learn nearly nothing. And so this is Jaroslav Kurzweil. We will soon celebrate his 95th birthday, hopefully. And then there is a book on the Kurzweil-Stirjes integral. One of the authors is Giselle Monteiro, my co-author. And yeah, and I will finish with the list of references. The preprints, we have uploaded some new versions of the preprints because the old versions were full of small errors and discrepancies. I hope that the new versions are now correct and with no substantial errors. Okay, and that's it. Thank you very much.
Thank you, Pavel.